When dealing with a continuous random variable, oftentimes we're going to be able to calculate the probabilities that we need to work with using the distribution function or the cumulative distribution function. Now, even though the cumulative distribution function is often easy to work with, there are going to be times where rather than characterizing the distribution through the distribution function, we want to characterize it through the density function. The density function is going to contain all of the same probabilistic information as the distribution function will. The only difference is that if we want to use it to calculate probabilities, we're going to first have to integrate. So the probability density function, or the PDF, if it exists, contains all of the same probabilistic information for a continuous random variable. Now, to use it to calculate probabilities, we have to integrate. So how do we take the PDF and use it to get probabilities? Well, the PDF is defined to be the first derivative of the CDF. So in our notation, capital F of x is going to be the CDF, right? You take the derivative of that, that gives you lowercase f of x, which is the PDF, or the density function. Now, the properties of the PDF are such that it is always positive, or at least non-negative, right? So 0 is less than or equal to the PDF for all possible values of x. And if you take the integral over the entire real line, you're going to end up with 1. So the density integrates to 1. And with those two properties, we define a valid density function. And then what we can say is that given this density function, if we want to know the probability that x falls into any set at all, so here we're taking x being a member of A, where A is some set, right? Then this probability is given by taking the integral over that region of our density function. So more practically, if we take A to be an interval from A up to B, right, then the probability that x falls between A and B is going to be the integral from A to B of the density function. And so ultimately, once we have an event in mind, we can express that event as some set A. And what we need to do then is actually integrate our density function. And by integrating the density function, we're going to wind up with a probability. So ultimately, when you're using the density function in order to solve for probabilities, what you need to do is turn to integral calculus. You solve these integrals. The integrals that you're solving end up giving you probabilities. So let's look at some examples here. So in this first example, we have a manufacturer who's manufacturing chemicals that can be of different qualities. And the quality is going to end up being a number that is sort of centered on 100, but falls anywhere between 80 and 120. Where higher qualities are presumably preferable. The true quality is going to be governed by this probability density function here. So we have f of x is x minus 80 divided by 800. And again, x can take on any value between 80 and 120. And so in other words, the density is 0 outside of those locations. In part A, we want to know what is the probability that the chemical has quality exactly equal to 90. And so if we think about what we're actually talking about here, right, we want the probability that x is equal to 90, right? But remember that x here is a continuous random variable. And anytime we're dealing with a continuous random variable, the probability that it equals some value specifically is always going to be exactly 0. So this probability in part A, because x is continuous, is simply going to be 0. Okay. Now, what about the sort of more interesting quality? What's the proportion of batches, or the probability that a batch has a quality that is less than or equal to 90? And so here, we want the probability of x being less than or equal to 90. Now notice that if we had the CDF, then in this case, this is just simply going to be f of 90, right? It's the probability that x is less than or equal to some value. But we don't have the CDF. We're just dealing with the PDF here. And so what can we do? Well, what we need to do is we need to integrate over the range that we're discussing here. And so that's the range of x being any value from negative infinity up to 90, right? That's the interval we're thinking about here. And we integrate the density function here. So that's fx dx. Now, in practice, we know that the density function is 0 if it's below 80. So this simply becomes the integral from 80 up to 90, and then we can plug in our density here, right? So that is going to be x minus 80, divide that by 800, and then we take that integral with respect to x. And solving this integral right here will give us the probability, okay? So we can walk through that here. Because we want the probability that x is less than or equal to 90, then we can set this up as an integral expression, right? The probability that x is less than or equal to 90 is the integral from negative infinity up to 90 of fx dx, right? Plug in our density here, and that gives us the integral between 80 and 90 of our PDF right here. If we solve that, we get x squared minus 160 times x, all divided by 1600. That's evaluated between 90 and 80, right? And so if we do that evaluation, we should find that the answer here is 1 over 16. So there's a 1 in 16 chance that the quality is below 90, or between 80 and 90, right, equivalently. Now, part C, find the probability that the quality is less than k for some arbitrary value of k, right? So what we want here is the probability that x is less than or equal to k. And note that here, all we're talking about is simply the CDF at the value of k. Okay, and the CDF is always going to be thinking about this interval, right, from negative infinity up to, say, k in our notation right here. And we want to know what's the probability that x falls into this interval. And so then by definition, that's the integral from negative infinity up to k of our density function with respect to x. Okay. And so then in our case here, right, again, we can drop that negative infinity because we can never be below 80, or it's always 0 below 80. So that's 80 up to k. And then fx dx is 80x minus 80 divided by 800 with respect to x. And so then if we solve this integral here, what we're actually getting out is our CDF. Okay? So walking us through that again, right? We want to find the probability that the quality is less than k for an arbitrary k. So we take the integral from negative infinity up to k of our density function, right? Doing this, it simplifies down to the integral between 80 and k of the PDF plugged in, right? That gives us that x squared minus 160x over 1600 evaluated between 80 and k, right? And if you simplify that down, you get k minus 80 squared divided by 1600. And just to ensure that what you get makes sense, right? If we plug in the lowest possible value here, and it's an 80, we get 80 minus 80, it's going to be 0 squared over 1600, and so that gives us a 0 on the lowest end, which is exactly what we should see. And if we go up to 120, right, we plug in 120 here, we're going to get 120 minus 80, which is 40. 40 squared gives us our 1600, and so then we'll end up with a 1 on the upper end. And that's exactly what we should see with the CDF, and so while that doesn't confirm that we did the integral right, that is one way of checking to make sure that we're getting something that makes sense out on the other end. Taking a look at another example here, we have a particular fungus that has a lifetime governed by a particular density function here, and that density function is going to be 81 divided by x plus 3 to the power of 4, and it's defined for all positive values of x. Now, what's the probability that this fungus survives for more than 3 years? Right? And so here, what we want to look for, right, is the probability that x is greater than 3. And so there are sort of two approaches that we can take to this problem. The first is noting that we're talking about an integral here from, say, 3 up to positive infinity, right? And so to solve for this, we can take the integral from 3 up to infinity of fx dx. Okay, and this is going to work for us. We'll have to solve our improper integral here, but that's okay, right? We can use our limits to work that out. The alternative is going to be to recognize that the probability that x is greater than 3 is going to be 1 minus the probability that x is less than or equal to 3, right? And this probability we can now take as the integral, right, technically from negative infinity up to 3 of fx dx. But the nice part about our PDF here is that we know it's only defined as greater than 0 for positive values. And so that's going to be equivalent to 1 minus the integral, and we can integrate from 0 up to 3 of fx dx. Okay. And so these are going to give you the same answer no matter what you do, right? This first one is sort of more direct. It's following the definition exactly. In the second one, we avoid needing to take the limits in our integral. So either approach will give you the correct answer here, but we can see that worked out in full. Right, so we want the probability that x is greater than 3. We can either integrate 3 to infinity of our density function here, right? Or we take 1 minus the probability that's less than and integrate from 0 to 3 of our density. Okay, taking that secondary approach here, right, we take 1 minus the integral here. This integral simplifies down to 81 divided by negative 3 times x plus 3 to the power of 3, right? we're evaluating that from 0 up to 3. And if you do that, it simplifies down to 1 over 8. So again, you should find the 1/8 whether you do this directly or indirectly. But in this case, the probability that the fungus survives for more than 3 years is 1 in 8. Okay. Now, what is the probability that this fungus survives between 1 and 3 years? Okay, and in this case, right, we're dealing with simply a fixed interval here. So we have the interval from 1 to 3. We want to know what's the probability that we're in this interval. So the probability that 1 is less than or equal to x is less than or equal to 3 is always going to be the integral from 1 to 3 fx dx. Right? And so then if we plug in our actual expression here, right, that's the integral from 1 up to 3 of 81 divided by x plus 3 to the power of 4 dx. Okay, and we solve this integral, and then that's going to give us our probability directly. Okay, so once again, we integrate over the region of our density, and that is going to give us what we need. So we want the probability that x is between 1 and 3. Integrating, right, we plug in, we get the same integral that we solved on the last slide. X this time is being evaluated between 1 and 3. And if we solve that, we're going to get 19 out of 64, or about 0.297, right? So 29.7% chance that the fungus survives between 1 and 3 years. Finally, we can ask ourselves, well, what's the probability that the fungus survives for less than 1 year? Okay, and so in this case, we want the probability that x is less than 1, right? Which we could, again, set up as the integral from negative infinity up to 1 of fx dx. Now, we know that the smallest possible value is the 0, right? So 0 up to 1 of fx dx, and fx is 81 divided by x plus 3 to the power of 4. Okay, and so solving this will work out. The other thing that we can take a note is that we know that 1 has to be equal to the probability that x is less than 1 plus the probability that 1 is less than or equal to x, which is less than or equal to 3, plus the probability that x is greater than 3, right? And the reason that we have this, right, is that x is either less than 1, between 1 and 3, or greater than 3. Those are the only 3 possibilities for x. And so if we add them up, we have to get 100% probability. And the reason that this is helpful is because in part 2, we worked out this probability. And in part A, we worked out this probability, right? So that's from B, that's from A. And so then, in other words, what we could do, if we wanted to, is we could simply take 1 minus the probability from A minus the probability from B. And that's going to give us the same thing as if we solve this integral right here. Okay, and so either doing the integral or solving this directly will give us the probability that we're looking for here, right? Even though we're integrating PDFs for the probabilities here, they still behave exactly like any other probability, so all of our probability rules still have to apply. So we could take that integral, or we could recognize that these 3 probabilities added together have to give us 1. And as a result, if we take 1 minus 1/8 from part A minus 19 over 64 from part B, that's going to give us 37 over 64, which is our answer here. So again, whether you solve that integral or you solve it through your probability rules, you're going to end up in the same answer. Another example here, we have a certain part that's being manufactured, and it can have errors in the length of it, in terms of its length when we're manufacturing it. The errors are going to be random, and they follow the given probability density here, where we have f of x being e to the negative x divided by 1 minus e to the negative 1. And these errors are going to be between 0 and 1 unit long. Okay. So what is the probability that a given error is less than 0.2 millimeters, right? So we'll assume here that the errors are measured on the millimeter scale. And so again, we want x being less than or equal to 0.2, right? Which is going to be the integral from negative infinity up to 0.2 of fx dx, right? Which is going to be the integral in this case, because we cannot have errors less than 0. That's going to be 0 up to 0.2 of fx dx. Okay, and we could plug in our actual density here. Right, the density is e to the negative x over 1 minus e to the negative 1 dx. We solve that integral, and that gives us the probability that we're looking for, right? So with that, we can take a look at our actual calculation here, right? To get this, we're going to integrate, and if you do that integral, then you should find that it's about 0.2867 0.64. Okay, so 28.7% chance that the error is less than 0.2 millimeters. Now, if we have a specification is that the error has to fall between 0 and 0.3, what is the probability that the specification is met? And so here, right, what we explicitly want is we want the probability that 0 is less than or equal to x, which is less than or equal to 0.3. And so we can simply integrate here our density over that given range, right? So that's the integral from 0 up to 0.3 of e to the negative x, 1 minus e to the negative 1 dx. Right? And solving that integral is going to give us the probability that we need. Right? The integral is going to be very similar to the one that we just solved up in part A. In this case, we're integrating or evaluating the integral at 0.3 and at 0 instead. Okay, so taking this integral, we find that that's about 0.41002. So 41% chance that specification is met if this is what the specification requires. Now, we take one last example here. In this case, we're dealing with a random variable that has the given density function. And importantly, with this density function, we have f of x being c divided by x squared plus 1, where c is some unknown constant. We're defined on the entire real line here, right? So we have x being anywhere between negative infinity and positive infinity. Okay, so here we haven't actually been given the complete specification of the density function. And so the first part of this question is going to ask, well, what is the value of c here? Now, remember that there are two critical components to our density function. The first is that for all values of x, we need f of x to be greater than or equal to 0. And what this tells us in this case is that c is going to have to be greater than or equal to 0, right? If c is a negative value, then we end up with negative densities, and that's no good. So we know that c can't possibly be a negative value, but beyond that, it doesn't tell us a whole lot. And so the other trait that we know needs to be satisfied is that 1 has to be equal to the integral from negative infinity to positive infinity fx dx. Okay, and so then in this case, right, if we just simply plug this in, that's going to be the integral from negative infinity to positive infinity of c divided by x squared plus 1 dx, right? And if we remember our integrals here, right, the integral of 1 divided by x squared plus 1, this integrates to be the inverse tangent, right, arctan function. Okay, and so if we have the integral here, then this is going to be equal to c times by our arctan function, and arctan is going to be evaluated at x is equal to negative infinity and x is equal to positive infinity. Okay, and so then we have to remember, well, what are the properties of our arctan function here? And I will just erase our note up here, and we can move upwards with this, right? So then the arctan function is such that in its limit, as it goes off to positive infinity, it's going to equal pi over 2, and as it goes to negative infinity, it's going to equal negative pi over 2. Right? We have those two asymptotes there. So that's going to be c times pi over 2 minus negative pi over 2. Okay. And so pi over 2 plus pi over 2 just gives us pi. So that's c times pi. Okay. And so in other words, what we have is we know 1 has to be equal to c times pi. And so this tells us that c has to be 1 divided by pi. Okay. And so again, what we're doing here is we start from our two properties. The first tells us that from positivity, we know that c has to be a positive value. Of course, 1 over pi is going to be positive, so no worries there. The other property is that it has to integrate to 1, and so we solve through our integral here. In this case, we need to remember some integral identities, but solving through those integral identities tells us that we end up with c times pi. Okay. If 1 is equal to c times pi, then c has to be 1 over pi. Okay. So walking through this argument again here, what is the value for c? Well, we know that it needs to integrate out to be 1, right? We end up with the integral equaling c times pi, and so as a result, c has to be 1 divided by pi. Now, given that c is 1 divided by pi, what is the probability that x squared lies between 1/4 and 1? And so in other words, we want the probability that 1/4 is less than or equal to x squared, which is less than or equal to 1. And so for us, right, we don't know what the density of x squared is going to be, so we need to find some way to express this in terms of x instead. And so if 1/4 is less than or equal to x squared, which is less than or equal to 1, right, then what can we say about x? So the first thing that we could do is we could simply just try to take the square roots here, right? So we square root of 1/4 less than or equal to x less than or equal to the square root of 1, which tells us that 1/2 is less than or equal to x is less than or equal to 1. Okay, and so that's one piece of this. The thing to remember, though, is that we can also take the negative square roots. And if we take the negative square roots, then we are going to want to flip the inequalities. So the other option here is to get that negative 1/2 is greater than or equal to x, which is greater than or equal to 1. And so in other words, what we're saying is that if x falls between either 1/2 and 1, or between negative 1/2 and, that should be negative 1, then we're going to end up with x squared falling between 1/4 and 1, right? That's where in this range we have that being the case. And so this probability is the same thing as saying, well, what's the probability that 1/2 less than or equal to x less than or equal to 1, or, so we can take the union, negative 1 is less than or equal to x, which is less than or equal to negative 1/2. Okay. And so because we have the union of two disjoint sets here, this is going to be the sum of both of these. So that's the sum, x less than or negative 1 less than or equal to x less than or equal to negative 1/2, plus the probability that 1/2 is less than or equal to x is less than or equal to 1. Okay. And then through these two probabilities, both of those can be written out using our integrals, right? And so that's going to give us the integral from negative 1 up to negative 1/2. And then our PDF here, remember that c is 1 divided by pi. We found that in part A. So that's going to be 1 over pi times x squared plus 1 dx plus the integral from 1/2 up to 1 of the same thing, 1 over pi times x squared plus 1. Okay. Both of those integrals are going to be arctan, and so then it's evaluating arctan at all of the endpoints and taking that all in together. Okay, so that's going to be how we can calculate out that probability. So what does that actually end up resulting in here? So we require x being either between negative 1 and negative 1/2, or between 1/2 and 1, right? And so if we work this out, then we find the two separate integrals here, right? We take in our arctan at both of these results. And if you solve through what this actually works out to be, that's going to be about 0.204833. So there's about a 20.5% chance that the square of our random variable, that x squared, falls between 1/4 and 1. And again, we can get through all of this using our density function by integrating over the correct regions. So to calculate probabilities using just the probability density function, we can turn towards integration. By integrating the density over the correct region of interest, then we're able to find our corresponding probabilities. So the density function still contains our probabilistic information, but in order for us to access that correctly, then we need to be using our integrals over the correct regions that we actually care about.